So in the previous video, we took a look at how we can actually define u for a u-substitution. And in today's video, we're just going to cover two quick examples of how to actually use u-substitution in order to evaluate indefinite integrals. And so these examples are going to be a little bit more advanced than the ones that we looked at previously, because I'm hoping that by now we're starting to get a little bit more comfortable with u-substitution. And so let's go ahead and actually do that. So over here, this first one is actually taken from an IB HL math question. And essentially it's the indefinite integral here of t squared times the square root of 1 minus t dt. So now our variable of integration is t. It's no different from x. Don't really get concerned about that. That's just a different variable. And so now over here, there's two ways we could look at this. I mean, we could think maybe this, t squared over here could be used as our u. But if you try that out, you're going to end up with a very complicated expression, because how are you going to end up with du over here if you set t squared to be equal to u? And so the other way we could approach this is maybe looking at this radical over here, and we have a 1 minus t inside of the radical. So if you would like, what we could do is we could try setting u to be equal to 1 minus t. And then we can get a couple of equations here. So if u is equal to 1 minus t, then what does that make t equal to? Well, then t is going to be equal to 1 minus u, right? And then next thing we can do is we can go ahead and differentiate both sides. So du by dt is equal to just -1, right? Because you differentiate both sides. And so that tells us that du is equal to negative dt. And so now we have all of our necessary equations. Let's go ahead and start substituting. So over here, this is going to become the indefinite integral of, instead of t squared, we said that t is equal to 1 minus u, so t squared is just going to be 1 minus u squared. And then over here, we have the square root of 1 minus t. Well, we said that 1 minus t is just u, so this becomes the square root of u. And then dt, well, if we'd like to replace this dt with du, then we just need to put a negative sign on the outside, and then a negative sign on the inside, and then that becomes du. And so now we have this expression over here. So the next thing we can do is we can go ahead and just expand out this 1 minus u squared over here. So we get negative integral of, this is just going to be u squared minus 2u plus 1 times u to the 1/2. I'm going to write it as u to the 1/2 just to make it look a little bit easier when we're doing the reverse power rule. So this becomes the negative integral of, we can just expand everything now. U squared times u to the 1/2 is just going to be u to the 5/2. Negative 2u times u to the 1/2 is just going to be u to the 3/2. And then plus 1 times u to the 1/2 du. And so then we can go ahead and just do this integration process. So here, this is going to become u to the 5/2 is going to become u to the 7/2. And then when we divide by 7/2, we get 2/7, right? So 2/7 times u to the 7/2. Negative 2u times u to the 3/2, we get u to the 5/2, right? And then when we divide by 5/2, we get 2/5. So this becomes negative 4/5 u to the 5/2. And then this over here is just going to become 2/3 times u to the 3/2, right? And then we can add this plus c over here. And now the final step, we can expand out this negative sign as well, and we can replace u with 1 minus t because we want our expression to be in terms of t now. And so we get negative 2/7 times, instead of u, we have 1 minus t to the 7/2 minus, but then this becomes a plus, right? So plus 4/5 times 1 minus t to the 5/2. And then this one becomes a negative sign now. 2/3 times 1 minus t to the 3/2. And then we have this plus c that just remains unchanged. And so this right over here, this is our final answer right over here. It's a very ugly box, but yeah, that's the final answer. It's a little bit of a complicated expression, but go ahead, try differentiating this and then doing a little bit of algebraic manipulation, and you'll see that it actually is the antiderivative. And so next up, we have a little bit of an easier question. This one actually came from the MIT Integration B entrance exam. And so let's go ahead and actually take a look at this problem. So here we have a rational expression. We have x plus 1 in the numerator. We have x squared plus 2x plus 3 in the denominator. This one can't be factored, right? And then what we can do is we can just go ahead and, instead of thinking about factoring, we can go ahead and actually think about using a u-substitution over here. So this expression over here is a little bit irritating in the denominator, but x plus 1 looks like it could be manipulated in a way that we get the derivative of this denominator here. So let's just go ahead and see what happens when we set u to be equal to x squared plus 2x plus 3. Right, because that could really simplify this process. And then du is just going to be equal to 2x plus 2 times dx, right? Dx is multiplying the whole expression, by the way, but I just didn't put parentheses. And so we have these two relations over here. And so what we can do is we can just go ahead and begin substituting. So in the denominator, instead of x squared plus 2x plus 3, we're just going to have u. In the numerator, we have x plus 1, and du is just 2x plus 2. So that's just going to be 2 times x plus 1, right? But if we multiply by 2 on the inside, we have to divide by 2 on the outside. And then here we have the dx. Well, this entire expression over here, 2x plus 2 times dx, is just going to be equal to du. So this becomes 1/2 times the integral of 1 over u du. And now this is much, much simpler. We just have 1/2 times the natural log of the absolute value of u, and then, of course, a plus c, excuse me. And then we have 1/2 times the natural log of, instead of including these absolute values, right, because u is always going to be positive, just x squared plus 2x plus 3, that's always positive, so we don't really need the absolute value. And we're just going to substitute u back in terms of x. So the natural log of x squared plus 2x plus 3 plus c. And so this right over here is actually our final answer. And I hope this made sense. I hope I wasn't going too fast. Re-review these examples and look at different examples of different integrals that you can solve using u-substitution. Get very comfortable with this notion because it is a very important method of integration and one that we're going to use pretty much throughout our entire integral calculus playlist.